Hi guys, am I audible to you?
Yes, sir, you're audible.
So good morning all. So I hope we can continue. So just to recap what we were doing. Um, give me a minute. So we were trying to look at the control system design or performance definition of the performance from frequency perspective. So the reason here is that this is another approach practiced by a well-known school. So somebody, as I always mention, in any input or output, U or Y can be considered as a signal with certain periodicity. There's nothing, you won't get straight line anytime. So you would see some oscillation somewhere, anywhere. So, but essentially means that this frequency is, there is some frequency associated with it, and this you can use this analysis to design a control system or getting insights from the system, and which could be further used for designing the process control systems. So the key aspect is, okay, you have time domain, you have Laplace domain, then you have f of t, L of f of t, and the third is h of w or L of w, whatever. So this is the time domain, this is the time domain, Laplace domain, and the third is the frequency domain. So frequency, to obtain frequency domain expression, you just need to put s is equal to j omega in the Laplace function or the Laplace transfer function that we all know. And we also kind of looked at why this is happening because of the connection or synergy between what you call Fourier transform and Laplace transform. Because of their what you call some of synergy, we are able to attribute this connection. And once you do that, oftentimes in the frequency domain, your coordinates of representation. So your specification. So in the time domain, your specification is maybe ODE. In the Laplace domain, your specification is transfer function. While in the frequency domain, your specification is amplitude ratio and phase lag, AR and phi. Amplitude ratio, you know how to calculate, which is the real some square root of real part and imaginary part. This is tan inverse of phi square. So how to obtain this? Again, you have to put s is equal to j omega, rationalize the transfer function, compute what we call how to rationalize, again multiply and divided by complex conjugate function. Finally, do an inverse. So what we call it, then extract out this term. This is your amplitude ratio. This is your phase angle. So now we were stopped. So this is what we were looking at previously, and the point that we were trying to make it how to represent now. So the point is how the representation became a problem, because if it is f of t, you can show a time versus some plot by the pressure or temperature or whatsoever. But like in frequency domain, what is the representation for? So here the various way of representation is basically something known as Bode plot and something known as Nyquist plot. So these are the two what you call representations of the, I'm saying schematic representation, because how to show the responses, which is not time versus some characteristics, but something else. So now we are going to look at that, and now later we will see how we would use these ideas for designing controllers and so on and so forth. So any issues at the moment before we go further ahead? Any issues? Are you all okay? All of you are with me?
Yes, sir.
Okay. So now we can just start looking at some of the what you call classical Bode plots of.
Sir, I'm unable to see your screen. Are you sharing it?
Is it possible? So none of them were visible, yeah?
I don't think it's not visible to me at least.
No, sir. Same to me.
I am extremely sorry about that. I was sharing it. Let me share and unshare. Thanks for sharing. Let me know if you could see my screen. Huh? This is what I was trying to say. Is my screen visible?
Yes, sir.
Okay, so maybe just to kind of just to kind of summarize what I told, I think See, time domain it is f of t, Laplace domain it is LFF of t, frequency domain is function of frequency. How to move from Laplace to frequency domain is substitute LFF of t would be some h of s. Let's assume that it is a transfer function, h is a complex variable, what you call the Laplace variable. How to move from, you know how to move from here to here, this is the Laplace transform. And Laplace to frequency domain is just s is equal to j omega, then you will be reaching here. You can also move from time domain to frequency, then use Fourier transform. And all their inverses. If you want to go back from here to here, use L inverse. Okay, and frequency domain to directly go back to the time domain, use inverse Fourier transform. Then this was the first point that I have mentioned. Now coming to the second thing, the representation in the time domain, which is f of t, mostly the representation is in terms of ODE. I don't know. Sometimes it makes. Let me open a new notebook better, I think. No, I think it's okay. So, so the representation in time domain, of course, is our well-known time series plot. You have time versus some variable pressure or temperature or flow, and you would see something over here. It may be something over there. Okay, but how to represent things in frequency domain, because your variables are no more time and no more anything else or anything, nothing is here. Okay, so because the argument here is omega or w, whatever you call. So there are two traditional way of representing frequency domain represent what you call graphical representation of the system. One is, I think I have written Bode's plot and Nyquist plot. Okay, Bode's plot is a two plot, so it is basically amplitude versus omega. Amplitude, let me also draw it very nicely. We will see. Okay, so amplitude ratio versus omega or phase angle versus omega. So because there are two arguments, right? Because when you do the s is equal to j omega, what you are eventually going to get is a complex number which is having a form of r plus j omega. Sorry, r plus ji. So this is the real part, this is the imaginary part. Okay, so now you can calculate the amplitude ratio by calculating the square root of sum of subsquares of the real part and the imaginary part, and the tan inverse of I by r would give you the phase angle. So you get two coordinates, but of course these are all varying with respect to omega. So what I'm trying to say, you won't get amplitude ratio as a fixed quantity. So your amplitude ratio would be a function of omega. Your phase angle will also be a function of omega. So it would vary when you plug in the value of omega. So how amplitude ratio varies with respect to omega, how phase angle varies with respect to omega, this is generally achieved by Bode's law. And it's also very important thing to check some stability. We will come to that at a later time. And there is also something known as Nyquist plot, which is a polar plot. Polar plot means you have a you have an argument and an angle. What you call sorry, the amplitude and its phase angle you represent as an argument. We will see how to plot it. So this is how Nyquist plot looks like. Nyquist plot is circular, and you will see something like this also. So this may be something like this, something like this. Here you see two distinct plots, one representing amplitude versus omega and one is phase angle versus omega. While the other one is more compact one representation. We will see that now. Now afterwards we will see how we will define some two performance indicators or two indicators that kind of simultaneously help to compute the performance as well as stability. So they are basically gain margin, okay, and phase margin. Again, they're all function of omega. That's why we are doing it in the frequency response. And we will the last step would be using this gain margin and phase margin how to design a controller. So this would be the subsequent step. Now we will look at this representation. Later we will look at the classical thing known as Bode stability criterion. And there is also a native stability criterion which we won't look into, but if you want, we can discuss that. But this Bode stability criterion is something that gives rise to the definition of gain margin and phase margin. So recall, for the previous case, we are using the stability definition BBO, right? Bounded input, bounded output stability. So see here, everything is in terms of frequency. So regardless of the input boundedness, we have to define some stability criteria in terms of the frequency. That is something that is basically the Bode stability criterion, which is much more stronger because it, and also see when we look at Rouse array and things like that, Rouse stability criterion, we have seen it. Rouse stability test, right? So what we will look at, we will look at the denominator transfer function. This is numerator, this is denominator. We look at the denominator polynomial and make the rows array and compute. But the problem here is that if things are not rational, in the sense that if there is a time delay term in the system, you will not be able to use round stability because we don't know how it is going to affect. Because the time delay when you take into the denominator, it will be another polynomial. So Bode stability criterion is independent of all these assumptions. It's more generic in nature. So that is why another reason we are we are also looking at the frequency domain, because something that is not explainable in the time domain, it has a very good insightful representation available in the frequency domain. So this is the reason. So are we all okay? Any questions? I hope now my screen is visible and all things are okay. Is it okay? Okay.
Yes.
So now let's look at the first aspect is looking at some of the
Sir,
Bode.
again it got unshared.
Oh, it's happening like that. Huh? So when I switch my screen, I think it's getting upside. Let me check. Very interesting. So it should be okay now. Okay, so Bode plot, as I told, it is a plot of amplitude ratio versus frequency, phase angle versus frequency, and we're also, because see, eventually these are all designers, right? Control practitioners. So they would also use some non-standard units, which is very, very convenient to them. So for instance, one of that is decibel. So 20 log AR is the decibel. Amplitude ratio in decibel. So the way how do you convert amplitude ratio into decibel? Why are we doing it? So that is the practice. So for instance, if you go to if you fill in a car, for instance air in the car. Okay, you cannot go and say I need to fill in this much Pascal pressure. So there, it is all PSI, pound. So we are not using LBS units anyway. We are all using SI units. But still the common man, so this is the way it has been practiced, we'll say, this much PSI unit. So million pound force per square inch, which is definitely not the standard. So we are so similarly for people who are traditionally working in this domain, so signal, one of the standard units that people use is decibel. So it may be, so sometimes people also used to represent the amplitude ratio as in terms of decibel with the conversion factor is 20 log AR. So now let's start to look at, this is whatever you see on the right hand side is a typical body plot. As I told, it contains two parts. Your part A contains amplitude ratio versus frequency. Frequency sometimes for simplicity, instead of omega, you may also take omega tau into account, so that your plotting would be easier. So in fact, it would be most of the time it is omega tau only. And similarly, phase angle, the three parts of the curve is phase angle versus omega tau. So now how are we getting it? It's very simple. So see, this is a log. This is log, this is logarithm, this is logarithm. So other one is semi-log. So this angle is log, and this is not log. Okay, so this is log and this is semi-log. Semi-log. Okay, so how to plot it? Again, very simple. So you we know 1 by tau s plus 1 is our first order system. Now see, go a couple of slides back. We have seen how to convert that into amplitude ratio and frequency. So, and maybe I'll just record that information again. So first order system, okay, 1 by tau s plus 1. You have to put s is equal to j omega to convert them into, so this is in the Laplace, okay, so you put this in, now it is in the frequency domain. So, but the frequency domain, what you would really see here is when you put s is equal to j omega, there is a denominator, the complex function. So j is coming in the denominator, so which is not rational. That is not the standard complex form. It should be r plus ij or r plus ji. So r plus j is the complex. What do you call it? J indicates the complex number. So how to do that? You have to multiply and divide by the complex conjugate. Of course, when you do that, you will be able to isolate the real part and imaginary part of it separately. So once you have the real part and the imaginary part separately, then r square plus I square, square root of that would give you the amplitude ratio. So tan inverse I by r, so would give you the phase angle. So now you have your phase angle available. Now you are ready to plot. Now you are ready to do the body plot. So now come back and see over here. Amplitude ratio is right here. Phase angle is right here. Plug in the value of omega tau and compute the AR. So you would see how, and just plot it in a semi-log plot. Why do you need a semi-log plot? Because for log plot maybe because so you have to represent all potential values of omega. So this potential values could be vary from how much? From 0 to very large number, right? Maybe 100,000, just to make sure that we are, whenever we are going close to the high end, because we are now looking at the perturbation of the system for various frequencies. Various frequencies essentially means that there will be no frequency and there is very high frequency. So both extent you should be able to cover. Okay, so if you're not start putting it in the normal graph, you will not be able to do it because your scales are limited. So log plot in that case is a easy solution. Okay, so this is whatever you see over here in terms of this what you call the solid line is something known as exact body plot. So exact body plot essentially means that you are more or less computing every point inside and plotting it. So there is also something on approximate body plot. Approximate body plot is basically is this, which is up to here and here. So you are just leaving this intermediary point. So how are we getting it? So you have to plug in omega is equal to 0, then the amplitude ratio is equal to 1. Then you would really see that when you start increasing the omega, there is no substantial change in the value of amplitude ratio. The point at which your amplitude ratio takes a turn, that is that particular frequency or that particular point is known as the corner of the graph. So when omega is 1 by tau, which essentially means that this essentially would get cancelled. So then you would see that from that point onwards, any further increase in omega would sharply change the curve. So you represent this corner point when omega is equal to tau. Then it's a linear relation. So because then the 1 here doesn't have any influence. So whenever, because now the 1 is a smaller number. So you keep on increasing it, then it would keep on what you call. So this particular term tends to dominate. Then you don't have to worry about it. So it would most likely behave linearly until over here for a large time. So you can take a very large number and plot, and this is your approximate body plot of amplitude ratio. The same applies for the phase angle too. Phase angle might stay constant for a long time. Then there would be a change. So this change would be mostly happening corresponding to the corner point. So this the frequency corresponding to that corner point of the amplitude ratio is known as corner frequency. So corner frequency would happen when omega tau is equal to 1, which essentially means that omega is equal to 1 by tau. So this is the value of the frequency at the corner point. Okay. So if you look at the body plot of the amplitude ratio, you would see that there are two basic asymptotes. One is lying very close to two basic graphs. They are connected together. So this is the low frequency asymptote. When omega values are close to 0, and this is the high frequency asymptote when omega values are high, it's very high. So if you see this, you would really able to say that how the system responds. So what is the inference that you can see? So from by looking at phase angle, you forget about it. That is the amplitude ratio. For the smaller frequency system, it's not very responsive. It would just there is no significant response from the system. But when the corner frequency, which is 1 by tau, when it becomes more than corner frequency, the system is showing a very rapid response. So this is the inference that you would take home from this body plot. So when you see a body plot, this is what this is the inference that you would like to take home. So this is a typical example of first order. Now we will see a couple of more examples. So before we go ahead, any confusion or any questions at the moment?
Also, could you please repeat that inference?
So the point what we are trying to say is when you look at, so you don't have to do any analysis. Okay, when you start looking at, so somebody has given you a body plot. So the important thing as a practitioner, you would look at, okay, so for the low frequency, the system is it is showing a very low response because the amplitude ratio is fairly constant. Correct. In fact, this is normalized amplitude ratio, which is A by A hat and K whatever. So there is no significant change in the system response until this corner frequency. So if you need to excite the system, okay, if you need something beyond that, you will have to move beyond this corner frequency. And the corner frequency, yet also to be careful when the frequency becomes high, the system responses amplitude is tend to magnify. So wherever you need to operate by looking at this corner frequency and the related points, you could be able to come up with a stable operating regime. Okay, so if you really would like not to do any experimentality, you can just take this inference. Okay, till this point, which is the corner frequency, whatever you do to the system, it doesn't going to make any harm. So if you are doing any experiment beyond it, be careful. Is that okay?
Yes, sir.
So I'm saying this is very different, no? So you would also be able to draw same level of inference looking at the gain and time constant from a Laplace transform. But here, a very like an analogous inference is made by looking at the frequency of the system. That's all. That's the point. Is that okay? So this is what the take home message. So now coming to the so see, we have learned about transfer functions within. So let's look at some transfer function, some more transfer function, and see, and let's try to rationalize how their frequency response looks like. Again, by using Bode plot. Of course, you can use Nyquist plot also. We will see one example towards the end. But I think this is more quick and ready reckoning. So because the point is that this is uncluttered, right? So you have to independent information available in front of you, and you are free to make any decision. Are you all with me? Ashutosh, Deepak, Devendra, Hemant, Paras, Rahul, Rakshi, Samuel.
Yes, sir.
Yes, sir.
Okay, guys. So now let's look at how an integrating system behaves. So what is integrating system? Integrating system has a transformation of k by s, which is essentially 1 by s times some k. So now let's look at this is exactly so let's look at how integrating system behaves. So if you need to compute the amplitude ratio of the integrating system again k by jw, you have to multiply and divide it by j. So eventually you would get the amplitude ratio to be k by omega and phase angle tan inverse because there is no imaginary part, sorry, real part in it. So I by r, real part becomes 0, it would be infinity, tan inverse of infinity is minus 90 degrees. So what is that you see here? So integrating system, you know how the behavior looks like. Even if it is time with respect to s, it keep on increasing or decreasing whatsoever. So see, it is also, so you see analogous response over here. So the input frequency changes, you get a linear thing. So whenever you change the frequency as a function of amplitude ratio, you see that you analog. So what I am trying to say, this is like this. This is the mirror, and you put your Laplace thing over here, and your frequency response over here, and you are saying the same thing. You are going to see the same thing. No difference in the extent. So this is a classical example of that. You or even FOP. So we are not saying drawing any. We might draw any additional information, but we won't kind of object any inferences obtained from any other. So basically, what I am trying to say is Laplace domain suggests you something. Frequency domain never objects that. You will also get the same thing. So maybe you might get more in what you call inside information. For instance, what is the frequency till which it behaves, what you call fairly constant, and so on and so forth. But these what you call these sources of information one and two never contradict each other. So they are all going to be the same. Is this okay? Shall I move ahead?
Sir, why do we only get infinity as our angle?
Okay, it's very simple, no? So tan inverse I by r, no? What is the, so if you look at the k by s, no, there is no real part in this.
Right, right.
So r is 0, no? So 1 by, so this becomes infinity. Why here it is a function of omega. So your phase angle is constant. So the response, the phase angle of the system is always constant. Only the amplitude going to change.
Yes, sir, understood.
Again, second order system. So we are now trying to see this chapter is a very interesting what we call summarization. So we have learned about all the dynamics, then all the controls. So this was dynamics, maybe a first 2-5 chapters, maybe I don't know. Then control remaining 6 to 9. Correct? So we are everything here we are going to summarize. So this is all in terms of the time and Laplace. And this is in terms of transfer function and so on and so forth. So now we are going to compare everything. So now we are all looking at this first order, second order system we have learned earlier, but we are now trying to see from the eyes of a frequency response analysis. Second order system, slightly more complex. Okay, in fact, very complex though. So you would really see that again, substitute S is equal to j omega. You do this analysis, you would get an tan inverse, compute what is real and imaginary part, do psi is equal, compute the amplitude ratio and frequency. You will get it. So the key point that you would like to share is the zeta is coming in here. So instead of, so zeta is an additional parameter here. Like we have seen there also, because zeta is something that controls our damping, you see. So if it is more or less, we have learned various categories for zeta. So same. So I'm saying we are getting exactly same inference, or as I told, the mirror image inference in the frequency domain. Okay, so because C zeta being an additional parameter, because in the amplitude ratio also zeta is coming in, phase angle is also, so zeta is coming in. So if you again plot the Bode plot, again slightly complex, you see, for this is the typical under overdamped and the underdamped system. Mostly, you see, overdamped system is fairly stable. You would also see how it looks. So in the overdamped system, it's most likely the response like this. And you would also see, so it eventually very close to first order system responses. You see, for different values theta, you are getting the different responses corresponding to beta. You can compute the slope also by substituting your value of omega close to infinity and isolating the variable. So this is how that slope comes in. So, but look at the underdamped case, you see there is some level of perturbation here. So underdamped system, we also know that it also doing a oscillatory response at some point of time. So this is the regime wherein that frequency get acted upon. Just maybe 0.1. So basically, so this in this basic regime. So you see for different values zeta, you would see different responses. Otherwise, they all behave the same. So if this, so again, so what I'm trying to say is this is the point where you see that oscillation finally dies out. So this is also that frequency regime what that generates that oscillation. Eventually, it dies out. Again, phase angle. We could see. I'm sorry about this. Let me just. So this is how the frequency basically phase angle. Again, no magic. Plug in the value of zeta and tau. First of all, fix the value of theta. For instance, it is 1. We keep the value of zeta is equal to 1. Vary omega tau and compute the tan inverse of that plot. No magic around it. So you will get this. So I'm saying there is a fundamental difference in terms of their characteristics, and this is how you should be able to work to get more interesting responses. So next is time delay. So time delay, of course, assume G of S is equal to e raised to minus theta s. Just making time delay. Of course, nothing interesting, but let's see how what is the response of the time delay, because S becomes j omega, right? So e raised to minus theta s you can write as a complex number cos theta minus j sin omega theta. So the amplitude ratio cos square theta plus sin square theta will be always equal to 1, and tan inverse would be minus tan inverse of this is tan, no? Tan inverse the tan inverse of this thing. So eventually it all cancels out and you will get minus omega theta. Tan inverse of minus tan theta. So how? So now somebody can tell me how the amplitude ratio looks like. Amplitude ratio would be a fair straight line. It is exactly opposite to whatever we have seen in the integrating system. Here amplitude ratio is varying, while the the phase angle is varying with respect to omega theta, omega.
So shouldn't the phi be minus of tan inverse of minus sine by cos?
I did not understand.
So shouldn't the phi be minus of tan inverse of the imaginary part by real part? So there should be an additional minus in front of the phi. So right in the time delay part.
Achha, so you are talking, no. So what is the question? So see the polar. So this minus is because of this negative is coming out.
Yes.
Not as not. So it is not as per the expression. I hope it's clear to you, right?
Yes, sir. So we can just the phi is fundamentally equal to minus of tan inverse of real imaginary part by real part.
No, just I by r. If I has if this inside argument has a negative, you can take it out. So it's like this. Now for any complex function, the phase angle is tan inverse of I by r, right?
Right, sir.
So, but if your inside argument somehow happens to be a minus, because see this phi, if you take a tan inverse, their responses are all in terms of n theta or n pi kind of thing, right? Just to avoid confusion, you can take that minus out and just compute the tan inverse of that inside argument. So this minus tan inverse of theta is coming just because of that. It's not by the definition.
Understood.
So here also, so here what is happening is again tan inverse of minus sin theta. This minus has come out. That is this minus. Sin is this is tan omega theta. Okay. Tan inverse tan cancel. This minus stays and omega theta comes back. This is, I hope this is clear, no? Any confusion on this?
No, sir, it's clear.
Okay, so you would see omega theta, of course, minus omega theta, but this is being plotted in a log framework. You see, initially when the omega changes, there would be little change in the phase angle, but when there is a significant change, you would see there is a. So omega theta is equal to 1, that would be your coordinate frequency somewhere here. Okay, so you can also do it for the PI controller. So PI controller, how do you do it? Again, substitute S is equal to j omega, do your rationalization, and leaving that to you, compute what is amplitude ratio or the phase angle. So phase angle and the amplitude ratio. So see, you would see a really opposite curve compared to PI controller, what you call first order system or second order system. You see that? So this is a slightly inference. I can tell you some take home message out of it. So what is a controller? Controller is technically an inverse of the model. You see IMC or so what we are doing is inverting the control. So see, are you getting my point? So if whatever model tries to do, controller tries to suppress that. Correct? So the model we behave mischievous or like show is mischievous, but controller would try to tighten it. Agreed or not agreed?
Agreed, sir.
So that is why very fundamentally the responses of the transfer function, which is upward cup, while the controller would have a inward cup shape. So whatever it does, it tries to compensate. So the fundamentally that's why you see a what we call nullifying response from here. See, for that particular frequency, what mischief that the process trying to do, the controller would try to do the opposite. So that things are in control. Okay, so now I will. Okay, so maybe around, and we can talk about couple of more. So any doubt on this overall body? So okay, so what you are expected now? So let's say if you are given with a transfer function, you should be able to draw a body plot, or you should be able to identify a corner frequency, low frequency asymptote, high frequency asymptote, possibly the slope of the low frequency asymptote or high frequency asymptote, because this expression. So this is of course not this is not an exclusive list of models, right? You can have anything. Is that agreed? So if you are given with a new transfer function also, you should be able to compute the AR and phi expression and take out the inferences. If it is plotting, you plot, or compute the corner frequency, omega tau is equal to 1 whenever there is a jump that you would see. Okay, then what else we can, so compute the low frequency asymptote, high frequency asymptote, and maybe or compute the slope of them. So what is the slope of low frequency asymptote? Compute the frequency of the high frequency asymptote. So I hope this much you should be able to do. Any questions at the moment? So I am trying to say these are not exclusive list of things that you would do. Given a new transfer function, you should be able to do these things independently. Is this agreed or not agreed? Are you okay?
Yes, sir.
Okay, so now coming to the second aspect of representation. So some people, and like this was of course a bit more, I think, much more newer, what you call, compared to the body. So body was a bit more older as far as I understand. So next is a slightly more newer approach for representing the what they call the frequency response. So one is, I think, so if you look at the body plot was an older thing, so maybe in 30s, or while Nyquist plot was close to 50s, 60s. This is what my understanding. Okay, so why the Nyquist plot came? So body plot was good enough, no? It is kind of giving you enough information. So, but again, the cumbersome pain point here is that there are two things you have to simultaneously looking. It's not a good, it can be a good thing, of course, can be a bad thing. Basically, the bookkeeping efforts are more here because you have a amplitude, because graph, let's say, so two, and any decision should be a joint decision based on the looking at together. So what Nyquist proposed, okay, that kind of get rid of the two steps, no? Okay, we can embed the same set of information just using a polar plot. So I hope you know a polar plot of a complex number. I hope you recall what is polar plot, correct? You have the argument and the angle together represented in the same plot. So that's why it's called polar plot. So while these are two independent parameter plots, so you have both are plotted as a function of omega tau. So these are, but while the second one is more compact because it's a polar plot of the. See, the point is, so you have to understand, right? So once it is a function of j omega, so then you are transferring all your load to the complex arithmetic. So if any tools in that domain you can fruitfully use. Correct. So you are now in the complex number. So complex numbers, so complex number analysis is a very, very rich field in terms of representation, in terms of computing. So many and so many, so many. So Bode used one aspect of it and represented, okay, let's do a parametric plot. Nyquist used another aspect of it. So is Bode plot seems to be complex to me because there are two plots. Let's embed the same information in the same graph. So because complex number, of course, you can make a polar plot. So the point is it's compact. That's the most important thing. So this is how a Nexus plot looks like. Again, the compactness also, the compactness also is one advantage. And so I would say this advantage of Bode Nexus plot is compactness. And I'll also say disadvantage of Nyquist plot is also compactness. So this is first order Nyquist plot. I hope it is first order. No, it's not first order. I'll have to check. So let's look at the first order Nyquist plot. So this is how it looks like. So it is compact because only one graph present. Because every information is embedded in this one circular and one circular thing. Then there is an arrow mark going on. Everything is there. So it is compact, no doubt. So as I told, it is compact. But for a naive person, this compactness has become disadvantage. So are you able to read things in both very quickly from Nyquist plot compared to the Bode plot? Could you? Can someone say?
So what is the question?
Pardon?
What are you asking?
Okay, so I'm saying this is the Nyquist plot of first order transfer function. You have your Bode plot also. Huh? Correct. So I am also drawing the Bode plot side by side. So this is our Bode plot. I'm going to draw over there. This is amplitude ratio omega tau, phase angle omega tau. Fine. This is Bode. So I am saying same information, exactly same information contained in A and B. Because it is a plot of a complex number, right?
Yes, sir.
So,
Say that just like in our Borders plots, when omega was going to 0, AR was going to 1. So here also we have the same thing. And when omega goes to infinity, AR goes to 0. So here also in Nyquist diagram also there is the same relation.
perfect. So everything is same. So this, I'm saying this 1 and 2 is compressed as 3. Everything. So as you rightly pointed out, omega is equal to 0, AR is equal to 1 because it's the coordinate is +1 and -1. This is again +1 and -1. So you are right here. Phase angle is 0 because the phase angle is calculated like this. Okay. Okay, and when AR is equal to, when omega tends to infinity, AR becomes 0, then your point is right here at the origin. Okay, phase angle is -90. So as I told, angle is calculated like this, so it would be -90 right here. So anything in between would be like this. So only problem here would be is the following. The readability may be little lesser for a naive person. So here can say this is the corner frequency, this is the region in which you have what you call the frequency is more affected, less affected. So even though the same information is embedded in the Nyquist plot, from the first site, extracting that may be slightly difficult. So of course, if you are practiced, there is no problem. You may be able to do. So that's what I told. The advantages of Nyquist advantage. The main advantage of Nyquist plot is its compactness because it compresses two curves into one. And main disadvantage is also its compactness. Are you with me? Are you okay? Any confusion at the moment?
No, sir.
Okay, so I will stop here, 21 slide, and the remaining, as I told, we would I will record and share you maybe today. So this would, okay, so let me just complete. So now what we are going to do something known as the body stability criterion. So I will just give an introduction and I will stop. What body stability criterion says, it provides extract. This is very important. Because if you are having a route stability criterion, and if there is a time delay system, if time delay is in the numerator, how to deal with that time delay? You have to use a time delay approximation, make that as a what you call polynomial and take into the denominator. So it is an approximate inference. So while body would give you exact result, so I'll talk about that. And of course, the body plot is more of a relative stability rather than an absolute stability that we will see. So the advantage here is it gives more exact result because no approximation here. Okay, and so just no approximation here. But again, this analysis is in frequency domain, while the other is in the Laplace domain. So if you have more time, you are interested to invest time in the frequency analysis, body stability criterion can be a good solution. So I will stop here. The remaining part I talk about the stability criterion and what I told as the gain margin and phase margin, and that's all. Maybe I'll make a half-an-hour video and upload again in the Teams itself. So with this, I think we would formally complete the content. Okay. Monday we will have the tutorial for this, and Tuesday we are having the pending quiz of the not this chapter, the previous two chapters, and we can have discussion on any queries if needed anytime. Is that okay, guys? And Wednesday and Friday, maybe forenoon and afternoon, anytime we can give full time for discussion. If to clarify any, I'm saying any doubt end to end regarding this course, so that you can be prepared well. Is that okay? All of you?
So, what would be the syllabus for the quiz?
We can have, so the not including this chapter, the previous two chapters. It is for I think which may be what is that controller design, basically controller design chapter and the closed loop synthesis chapter, two chapters.
Okay, sir.
Basically the tutorials there. But again, as I told, don't take it in that fashion because we are doing it incrementally. There may be some Laplace transform calculation you need to do. Make sure that you are primed up. Okay, then I'm wishing you a very happy festival season, Diwali, and so on and so forth, and enjoy your vacation. And let's see you on Monday for the tutorial for this session. I will upload the what you call the remaining 7 slides as a what you call as a video in the Teams itself. You can use it. And Monday let's do the tutorial, and remaining days let's do the quiz followed by revision. Okay. So Devendra wanted to say something.
No, sir, I'm good, sir.
Okay then, happy Diwali guys. Enjoy your day. Bye bye.
So happy Diwali to you too.
Thank you,
Please
sir.
upload the tutorial. It was
Uh,
important.
couldn't hear you.
Sir, I was saying the last tutorial was not uploaded. Tutorial 8, I think.
Oh, is that so? I'm sorry about it. Okay, so I will do ASAP. I'm sorry about it.
Yes,
Sir,
sir.
it's uploaded, I think.
Yeah, I can verify if it is there. You make sure that this is applied today. Okay.
Right, sir.
Thanks. Bye bye.
Thank you, sir.
Thank you, sir.